In science fiction movies, spaceships fly between stars in seconds, cross galaxies in minutes, and visit distant planets before dinner. It seems so easy and so real that we start to believe that one day we will do this too. But it turns out that the universe has very strict rules about speed, rules that no technology can break. Light travels at 300,000 kilometers per second, and that is the fastest anything can go in our universe. To reach the nearest star to the sun, even travelling at this impossible speed, it would take us more than 4 years. And here is the part that changes everything. The faster we try to go, the more energy we need. And near the speed of light, we would need infinite energy. This means that the spaceships in the movies, the ones that fly faster than light, are simply impossible according to the laws of physics. Prepare to fall asleep while listening to this video and discover why our universe places such frustrating limits on our ability to explore the cosmos. Subscribe to the channel. Leave your like and comment from what part of the world you are watching. Get comfortable and relax. Let's begin. Imagine dreaming of soaring through the galaxy at speeds that make stars blur into streaks of light, just like in your favourite science fiction movies. The truth is, our universe has a built-in speed limit that makes such fantasies impossible, and it all boils down to one fundamental law of physics. Albert Einstein's special theory of relativity established that the speed of light in a vacuum is the ultimate cosmic speed limit, approximately 300,000 kilometers per second. This isn't just a suggestion or a temporary barrier. It's a foundational principle woven into the fabric of space and time itself. Anything that possesses mass, from a grain of sand to a massive starship, can never reach this speed because doing so would require an infinite amount of energy. Think about that for a moment. Infinite energy isn't something we can generate. No matter how advanced our technology becomes, even if we could harness the power of every star in the galaxy, it still wouldn't be enough to push a single atom with mass to the speed of light. This is why particles without mass, like photons, are the only things that can travel at this maximum speed, and they can't go any faster either. You might have heard of creative ideas like warp drives or hyperspace jumps that supposedly allow faster than light travel in stories. But these concepts don't involve actually accelerating through normal space. Instead, they propose clever workarounds, like bending space-time or taking shortcuts through other dimensions. But even those are highly theoretical and face their own monumental challenges. The key point is that accelerating beyond light speed in conventional terms is as futile as trying to make 2 + 2 = 5. It defies the very logic of our universe. This speed limit isn't like the sound barrier, which we broke with better engineering. It's a hard stop imposed by nature. When objects move faster, period. Their mass increases from the perspective of an outside observer, thanks to relativistic effects. As you approach light speed, your mass would swell toward infinity, and so would the energy needed to keep accelerating. This isn't a gradual increase. It's an exponential climb that becomes insurmountable. For example, to get a spacecraft to 90% of light speed, you'd need more energy than humanity has used in its entire history, and that's just for a fraction of the journey. Beyond that point, each tiny boost in speed demands exponentially more power, quickly reaching levels that are physically unattainable. So, while science fiction often shows ships zipping past planets at unimaginable velocities, the reality is that we're stuck within this cosmic speed limit. This has profound implications for space exploration. It means that even the closest stars are years away at light speed. And since we can't reach that, trips would take decades or centuries. Imagine setting out for Alpha Centauri, the nearest star system. which is about 4.37 light years away. Even if we could travel at 99% of light speed, the journey would take over 4 years from Earth's perspective. But due to time dilation, the astronauts might experience only weeks or months. However, the energy required for such a trip is beyond our grasp. And the hazards along the way would be immense. Space isn't empty. It's filled with tiny particles like hydrogen atoms and dust grains. At near light speeds, these specks would hit the ship with the force of nuclear explosions, shredding any known material. Shielding against them would add so much mass that the energy needs would become even more absurd. Plus, the human body can't handle extreme accelerations. If a ship accelerated too quickly, the G-forces would crush the crew instantly, even at a comfortable 1g acceleration. Similar to Earth's gravity, it would take months to build up to a significant fraction of light speed and just as long to slow down at the destination. This rules out the quick jumps we see in movies. Moreover, the rocket equation tells us that carrying fuel for such trips is a vicious cycle. More fuel means more mass, which requires even more fuel, leading to spacecraft that are mostly fuel tanks. For interstellar travel, the fuel mass would be astronomical, like trying to fly across an ocean with a plane that carries all the water in the sea as propellant. Alternatives like ion drives exist, but they provide such gentle thrust that they're useless for fast, manned missions. Concepts like the Alcubierre warp drive propose contracting space in front of the ship and expanding it behind, but they rely on exotic matter with negative energy density, which might not even exist. The energy requirements for such a drive are equivalent to converting entire planets into pure energy, and it could unleash deadly radiation upon arrival. So, while it's fun to imagine bypassing the light barrier, the laws of physics offer no loopholes. This fundamental limit shapes our future in space, confining us to slow, generational ships or robotic probes if we ever hope to reach other stars. In the end, the speed of light isn't just a number. It's a reminder that the universe operates by rules we can't bend, no matter how clever we become. This doesn't mean exploration is hopeless, but it does mean we have to rethink what's possible, focusing on realistic technologies and patience rather than silver bullets. The silence from extraterrestrial civilizations might even be a clue that faster-than-light travel is unachievable, as no one has overcome these barriers yet. So, next time you watch a space epic, remember that the real universe is both more wondrous and more restrictive, with light speed standing as an eternal guardian against our wildest dreams. So, if the speed of light is this unbreakable rule, then the next logical question is, what does it actually take to get even close to it? The answer lies in perhaps the most famous equation in all of science, and it introduces a cost so astronomically high that it shuts down the dream before it even starts. Einstein's E equals mc squared isn't just a neat formula on a t-shirt. It's a brutal cosmic tax collector. That C stands for the speed of light, and because it's squared, dot, the number is unimaginably huge. This equation tells us that energy and mass are two sides of the same coin, and converting a tiny bit of mass releases a colossal amount of energy, which is how nuclear bombs work. But for space travel, it works in reverse, dot. To make something with mass move, you need energy. And as you go faster, the equation turns against you. As an object's speed increases, its relativistic mass increases too. This isn't science fiction. It's a proven effect. The closer you get to light speed, the heavier your spacecraft becomes from the perspective of the universe. This isn't just adding a few pounds. It's an exponential climb. To push that ever-increasing mass even a little bit faster, you need exponentially more energy. By the time you're approaching 99% of light speed, the mass is swelling toward infinity, and so is the energy required. It's not that we don't have efficient engines, it's that the universe demands an infinite price for a finite speed, and that's a bill no one can pay. Let's make this practical. Imagine we wanted to accelerate a spacecraft, something about the size of a modern aircraft carrier, to just 90% of the speed of light. The energy required for that alone would be greater than all the energy consumed by the entire human civilization for centuries. We're talking about harnessing power on a planetary scale for hundreds of years just for one ship to reach a fraction of the ultimate speed, not even considering the energy needed to slow down at the other end. This isn't a funding issue or an engineering challenge. It's a fundamental physical impossibility. The fuel simply doesn't exist. If you tried to use conventional chemical rockets, the amount of fuel needed would be so vast that the entire mass of the observable universe wouldn't be enough. Even if we dreamed up matter-antimatter annihilation, the most efficient process possible, the fuel mass would still be absurdly large. Think about a car trip where you need to carry fuel that weighs more than the Earth itself just to get to the next city. That's the scale of the problem for interstellar travel. This energy equation acts like a vicious cycle. To go faster, you need more fuel, but that extra fuel adds mass, which means you need even more fuel to push that extra mass, and so on. This spiral quickly becomes infinite near light speed. It's like a pyramid scheme where the returns diminish to zero just as you need them most. This is why scientists talk about the rocket equation with a sense of despair. It mathematically guarantees that we can't have compact, sleek starships like in the movies. The spacecraft would be almost entirely fuel tank, a sluggish behemoth struggling to move, not a nimble fighter. And this is for acceleration in a straight line in empty space, ignoring all the other dangers like radiation and particle impacts. The energy cost is so prohibitive that it makes the entire endeavour pointless from a resource perspective. Why would any civilization spend the energy output of a planet for millennia just to send one ship to one star? The return on investment is effectively zero. This isn't just about our current technology. It's about the laws of physics themselves. The universe has set a price tag on speed, and that price is infinite at the limit. So, when you see a spaceship in a movie effortlessly jumping to light speed, remember that behind that scene is an energy requirement that dwarfs all human accomplishment. It's not a matter of inventing a better engine. It's a matter of the universe saying no. This profound connection between energy and mass is what makes faster-than-light travel impossible, not just difficult. Even if we could somehow bypass the speed limit with warp drives or wormholes, those concepts have their own astronomical energy demands, often requiring hypothetical negative energy or the mass of Jupiter. So, the next time you look up at the stars and dream of visiting them, the biggest obstacle isn't the distance, it's the sheer, unforgiving energy cost dictated by E equals mc squared. This equation is the ultimate reality check, grounding our sci-fi fantasies in the hard truths of physics. It tells us that the cosmos is not designed for quick joyrides. It's a vast, empty expanse where the rules are strict and the tolls are unimaginably high. Our future in space will likely be slow, patient, and energy conscious, relying on generations-long journeys or robotic probes, not the thrilling hops depicted on screen. Understanding this helps us appreciate the real challenges of space exploration and directs our efforts toward what is actually possible, rather than chasing impossibilities. The dream of fast starships remains just that, a dream, because the math doesn't lie. And the energy required is forever out of reach. But let's play devil's advocate and imagine we somehow magically solved the energy crisis. inventing an engine that could propel a ship to 99% of light speed without requiring the mass of a star. You'd think we're all set for epic star voyages, right? Well, hold on. Because physics has another curveball waiting, and this one warps time itself in ways that are deeply personal and ultimately tragic for any would-be starfarer. This is the mind-bending reality of time dilation, a core prediction of Einstein's relativity that says time isn't a universal constant ticking at the same rate for everyone. Instead, it's flexible, and it stretches and compresses depending on how fast you're moving. For an astronaut travelling at a significant fraction of light speed, time actually slows down relative to everyone who is standing still. This isn't a philosophical concept or a perceptual trick. It's a physical effect that has been experimentally verified with precise atomic clocks on fast-moving jets and satellites. The faster you go, the more pronounced this effect becomes. To understand the sheer weirdness, let's take a concrete example. Suppose we aim for Alpha Centauri, the closest star system to our Sun, which is about 4.37 light-years away. If a spacecraft could cruise at 99% of the speed of light, the journey from the perspective of people on Earth would take roughly 4.4 years. That's the distance divided by the speed. But for the crew inside that ship, something astonishing happens. Because of their immense velocity, their clocks tick slower. For them, the trip might feel like it only lasts a few weeks, perhaps around 6 to 8 weeks depending on the exact acceleration profile. They would have aged only those couple of months, while back on Earth, over 4 years would have passed. Everyone they knew would be 4 years older. The world would have moved on, and their mission control team might have been reassigned or retired. This is the twin paradox in action. If one twin stays on Earth and the other travels at near light speed, the travelling twin returns being significantly younger than their Earth-bound sibling. Now, scale this up. What if the destination isn't Alpha Centauri but a star 100 light-years away, at that same blistering speed from Earth's frame? The round trip takes 200 years. But for the crew, thanks to time dilation, it might only feel like a couple of years. They could potentially make the journey within a single human lifetime from their own perspective. This sounds like a fantastic solution for exploration, doesn't it? Unfortunately, it's a poisoned chalice. The crew would return to an Earth that is 2 centuries into the future. Their families, friends, and the entire society they left behind would be long gone, replaced by a world they wouldn't recognise. Their knowledge, their skills, their cultural references would be obsolete. They would be living fossils, permanent strangers in their own homeland. This transforms what should be a triumphant return into a form of temporal exile. The very purpose of the mission becomes questionable. Are they exploring for the people who sent them? Those people are dead. Are they bringing back knowledge for contemporary society? That society no longer exists. The mission's original objectives could be utterly irrelevant by the time they report back. This isn't just a logistical headache. It's a profound psychological and social barrier that makes interstellar travel a one-way trip in every meaningful sense, even if the ship physically turns around. The travellers are effectively leaving their own time period forever. Imagine the personal cost. An astronaut says goodbye to their spouse and young children, promising to return after a journey they believe will take a few years. Due to time dilation, they experience only months. But when they come back, their children are older than they are, or have passed away from old age. The emotional devastation is unimaginable. No training could prepare someone for that level of loss and disconnection. This effect places a brutal limit on human spaceflight that has nothing to do with engineering and everything to do with the human condition. Science fiction often glosses over this or hand waves it away with suspended animation or cryosleep. But those are speculative technologies with their own massive problems. In a realistic scenario, even with a perfect engine, time dilation ensures that the crew becomes unmoored from their own timeline. This has dire implications for any notion of an interstellar empire or federation. There can be no rapid communication or coordination between stars. A message sent from Earth to a colony 10 light-years away takes 10 years to arrive, and a reply takes another 10 years. That's 20 years for a simple conversation. Governing a multi-star system would be impossible with such time lags. Trade and cultural exchange would be similarly stunted. Each star system would inevitably become isolated, developing independently over centuries, with the travellers acting as rare and tragic bridges across time. Furthermore, this isn't a symmetric effect. The crew on the ship experiences time slowing down, but from their perspective, it's the universe outside that appears to be in fast forward. They would watch as light from Earth shows events unfolding at an accelerated rate, like a movie on fast play. This could be mentally taxing. Watching your homeworld change drastically in what feels like real time for you. The isolation wouldn't just be physical, it would be temporal. You are out of sync with the entire cosmos. Now, consider the energy problem again in light of this. To achieve the speeds where time dilation becomes significant, you need that impossible energy we discussed earlier. So, these two problems compound each other. You need infinite energy to get close to light speed. And even if you could, you'd be condemned to a future so distant that your journey might be meaningless. It's a double bind that firmly slams the door on fast. Meaningful interstellar travel as depicted in films. The universe seems to be designed to keep cosmic neighborhoods separate. This temporal dislocation also affects mission planning. Who would sign up for a mission knowing they will never see their loved ones again? Not because of distance, but because of time. The recruitment pool would be vanishingly small. The funding and political will for a project whose benefits won't be seen for generations are hard to muster. It becomes a philanthropic endeavour for the far future, not a practical exploration for the present. Moreover, the technology on the ship would become obsolete during the journey. A computer system launched today would be antique by the time it reaches a nearby star, even from the ship's perspective, as technological progress on Earth continues at its normal pace. So, the data they bring back might be of historical interest only, not cutting-edge science. This time gap makes the concept of exploration fundamentally different from how we conceive it on Earth. When Magellan's crew circumnavigated the globe, they returned to a world that was largely the same. When Lewis and Clark explored the American West, they could report back to a president who was still in office. In space, relativity severs that immediate connection. The exploration becomes a message in a bottle, tossed into the ocean of time, with no guarantee that anyone will be there to read it when it washes ashore. This is why realistic plans for interstellar travel focus on generation ships or one-way robotic probes. A generation ship accepts the time dilation issue by having multiple generations live and die on the ship during the long voyage from Earth's perspective. But that's a colossal sociological and biological challenge, far removed from the sleek, fast starships of fiction. Alternatively, sending unmanned probes avoids the human cost. But then we lose the direct human experience of exploration, time dilation. Therefore, isn't just a curious footnote in physics. It's a central plot point in the story of humanity's place in the universe, and it tells us that we are forever rooted in our own time. The speed of light isn't just a barrier for velocity, it's a barrier for connection. It ensures that the stars, while visible, remain isolated islands in a sea of space-time, and that any journey to them is a farewell to the era you left behind. This profound understanding forces us to reconsider what space exploration means. Perhaps the future lies not in physically travelling to the stars, but in developing technologies that allow us to observe them remotely or even in virtual experiences. The dream of stepping onto an alien world might remain a dream, not because of a lack of courage or ingenuity, but because the universe is structured in a way that protects us from the heartbreak of temporal displacement. So, next time you see a spaceship warp away in a movie, remember that the real adventure would be fraught with a loneliness deeper than space itself, a loneliness of time. So you've accepted the mind-bending reality of time dilation and the heartbreaking temporal exile that comes with near-light speed. You're a dedicated explorer, willing to leave your own century behind for the sake of the journey. But just as you steel your resolve, physics unveils yet another showstopper, a danger so immediate and violent that it would vaporize your ship in an instant before you even got close to your target speed. We often think of space as a perfect, empty vacuum, a pristine highway for starships. But that's a dangerous illusion. The space between stars is not empty. It's filled with a diffuse medium of gas, mostly hydrogen, and tiny, microscopic dust grains. In our slow, local space travel around the solar system, these particles are a minor nuisance, but at relativistic speeds, they transform into a continuous dot, devastating barrage of ultra-high energy projectiles. Imagine you're driving a car on a highway and you hit a stray butterfly at normal speeds. It's a minor splat on the windshield. Now imagine hitting that same butterfly at 99% of the speed of light. The result isn't a splat, it's a cataclysmic explosion. This is because the energy of impact isn't just about the particle's tiny mass. It's about the kinetic energy, which scales with the square of the velocity. When you're moving that fast, every single atom of hydrogen you collide with carries a tremendous punch. A single proton, something you'd normally need a powerful microscope to see, would strike your ship's hull with the energy of a particle in the Large Hadron Collider. Now scale that up to a dust grain, perhaps the size of a grain of sand or even smaller, at relativistic velocities. That tiny speck would hit with the energy of a large nuclear bomb, releasing a blast equivalent to several megatons of TNT. It would be an impact so powerful it would instantly vaporize a significant portion of your ship, creating a crater of molten and vaporized material and flooding the interior with lethal radiation. Your vessel wouldn't just be damaged, it would be obliterated, turned into an expanding cloud of incandescent plasma. This isn't a risk you can take occasionally. It's a constant, unremitting hailstorm. Travelling at such speeds through the interstellar medium would be like standing in front of a constant, planet-shattering artillery barrage. Every single second of your journey, you would be enduring multiple impacts, each one capable of delivering a destructive force far beyond any weapon humanity has ever built. There would be no quiet moments, only the relentless, deafening silence of space punctuated by the simulated roar of atomic fireballs erupting across your hull. So, how do we solve this? The obvious answer seems to be shielding, but this is where the problem becomes exponentially worse. To protect against a 1 megaton impact, you wouldn't need a simple sheet of aluminum. You'd need an absurdly thick and massive shield. We're talking about a slab of material perhaps several meters thick, made of the strongest and most resilient composites we can imagine. Some have proposed using a shield of solid tungsten or even depleted uranium, but let's do the math on that. The mass of such a shield for a reasonably sized spacecraft would be astronomical. It would weigh millions of tons. And remember our previous discussions about the rocket equation and the prohibitive energy cost? This shield mass makes that problem infinitely worse. All that extra mass means you need exponentially more energy to accelerate it to near light speed, which in turn requires more fuel, which adds more mass, creating a vicious cycle that quickly becomes untenable. You'd end up with a ship that is 99% shield by mass, a sluggish, mountain-sized slab of metal that you somehow have to propel to relativistic velocities. The engineering is beyond comprehension. Furthermore, the shield itself would be constantly eroding. Each impact, even if it doesn't penetrate, would blast away tiny portions of the shield, slowly grinding it down over the course of the journey. By the time you reached your destination, your multi-meter thick armour might be paper thin, if it even survived at all. There are theoretical ideas for more advanced protection systems, like using powerful magnetic fields or lasers to vaporize particles before they hit the hull. A magnetic shield could potentially deflect the charged hydrogen atoms. But the neutral atoms and the larger dust grains would be completely unaffected by magnetic fields. They would sail right through a laser system, designed to zap incoming particles. Sounds like science fiction. And it practically is. The power requirements for such a system would be staggering. You'd need to detect and track every single microscopic particle approaching at near light speed and fire a laser pulse with pinpoint accuracy to destroy it, all within microseconds. The computer processing power and energy needed for this are far beyond anything we can conceive of, essentially requiring a power plant the size of a city dedicated solely to this defensive system. And even then, a single missed grain or a slightly larger than average particle would be enough to end the mission catastrophically. The margin for error is zero. This problem turns the vastness of space into a lethal shooting gallery. It means that the speed required to make interstellar travel feasible within a human lifetime is precisely the speed that makes the journey unsurvivable. You are trapped between the need for speed and the certainty of destruction. This isn't a problem that better materials science can easily solve. It's a fundamental issue of energy density and impact physics. The interstellar medium, which seems so thin and harmless, becomes an impenetrable wall when you approach the cosmic speed limit. This danger also has implications for any hypothetical alien civilizations. If they are out there, they face this same exact problem. The silence of the cosmos, the Fermi paradox, might be explained in part by this simple fact. The universe is filled with a faint, omnipresent mist that becomes deadly at high speeds. It's a natural quarantine, a cosmic filter that prevents any species from travelling too fast and too far. So, when you see a starship in a movie effortlessly cruising at warp speed, remember that in reality, it would be flying through a storm of nuclear fire, its hull glowing white-hot from countless micro-impacts, its crew living on borrowed time until the one particle it couldn't stop finally arrives. The dream of slicing through the galaxy at incredible speeds is not just limited by energy and time, but by the very substance of space itself, a substance that is far from empty and incredibly hostile to fast-moving objects. This realization forces us to accept that if we ever do travel to the stars, it will have to be at much slower speeds, where these particles are merely a minor abrasion concern, not an existential threat. It means our journeys will be long, generational affairs, where velocity is sacrificed for survival. The wall of bullets isn't a metaphor. It's a physical reality that guards the stars from rapid intrusion, ensuring that the cosmos remains a place for slow, patient exploration, not for swift conquest. The ultimate barrier to fast spaceships might not be a law written in equations, but a trillion tiny specks of dust, each one a potential bomb. waiting silently in the dark. Even if we could somehow engineer a shield capable of withstanding the relentless nuclear fire of interstellar dust at near light speeds, there is a more immediate and personal barrier that comes into play the moment you even think about pushing the throttle forward: the sheer physical force of acceleration itself. Science fiction has conditioned us to believe that starships can leap from a standstill to light speed in a matter of seconds, with the crew casually sipping coffee in their seats, utterly unaffected. In reality, such a maneuver would be the last thing those astronauts ever experienced, as their bodies would be instantly transformed into a gruesome paste against the rear wall of the spacecraft. This isn't hyperbole, it's basic physics. Acceleration isn't just about speed, it's about the rate of change of velocity, and the human body has very strict limits on how much force it can endure. We measure this force in Gs, where 1 G is the acceleration we feel due to Earth's gravity. Fighter pilots, for instance, train to withstand up to 9 Gs for short periods, which feels like 9 times your body weight is crushing down on you, requiring special suits and techniques to avoid losing consciousness. Now, imagine the acceleration required to go from 0 to a significant fraction of light speed in a few seconds. The G-forces involved would be astronomical, not in the single or double digits, but in the thousands or even millions. At those levels, every organ in your body would be subjected to pressures far beyond what any biological tissue can withstand. Your bones would shatter. Your blood would be forced to one part of your body, and your internal organs would be pulverized. It would be an instant, messy, and utterly fatal event. The ship might be capable of it, but the fragile bags of water and carbon inside most certainly are not. This is why any realistic spacecraft design for human travel must adhere to a very gentle acceleration profile for a comfortable and sustainable journey. The acceleration shouldn't exceed 1 G. This is the acceleration we are evolved to handle, the constant pull we feel every day standing on Earth. At 1 G, you would feel a sense of normal gravity, able to walk around, eat, and sleep without any ill effects. But here is the catch: accelerating at a safe, gentle 1 G imposes a brutally slow timetable on space travel. Let's do the math. If you constantly accelerate at 1 G, how long does it take to reach a speed that is a substantial fraction of light speed? It takes roughly 1 year of constant acceleration to reach near light speed. But that is just the acceleration phase. You also need an equal amount of time to decelerate at the destination if you ever hope to stop. So, for a round trip, you're looking at 2 years just for the speed changes, not even accounting for the coasting time in between. This immediately shatters the sci-fi trope of quick hops between planets. A trip to Mars, at its closest approach, would still take months under constant 1 G acceleration, not the days or hours often depicted. A journey to Jupiter would take over a year. This is because you spend half the time accelerating and the other half decelerating, following a trajectory that is far from a straight line at high speeds. The solar system suddenly becomes a vast, time-consuming place when you respect the limits of human biology. The notion of dogfights in space, with ships zipping and weaving at thousands of kilometers per hour, is pure fantasy because any sharp turn at that speed would generate lateral G-forces that would smear the crew across the cockpit. Inertia is unforgiving. A body in motion stays in motion unless acted upon by a force, and that includes the bodies of the astronauts. A sudden turn would fling them violently against the walls, resulting in catastrophic injury or death. There is no inertial dampener in real physics. That is a magical device invented by writers to ignore this fundamental problem. To cancel inertia, you would need to manipulate the very field that gives particles mass. the Higgs field, a technology that is so far beyond our current understanding it might as well be magic. Without it, high-speed maneuvers are a death sentence. This biological limit is as fundamental as the law of gravity or the speed of light. It doesn't matter how powerful your engine is. If you want to carry humans, you have to accelerate slowly and gradually. This means that even with ideal technology, travel times within our own solar system are measured in weeks, months, or years, not hours. For interstellar travel, the situation is even more dire. Accelerating at 1G, it would take you about a year to get close to light speed. But then you have to remember the time dilation effects we discussed earlier, and the sheer energy cost. However, the acceleration time alone adds a significant chunk to the journey. A one-way trip to Alpha Centauri under constant 1G acceleration and deceleration would take, from the perspective of the crew, roughly 4 years. But from Earth's perspective, over 6 years would have passed due to relativistic effects. This is a best-case scenario with a perfect engine, and it still involves a multi-year commitment for a one-way trip to the nearest star. The human body, therefore, is not just a passenger. It is the most demanding and limiting component of the entire spacecraft system. It requires a narrow band of temperature, pressure, radiation shielding, and now we see a very limited range of acceleration. This forces spacecraft designers into a corner. To make a ship fast, you need high acceleration, but high acceleration kills the crew. So, you must choose a low acceleration, which makes the ship slow. It is a trade-off with no happy medium for quick travel. This is why realistic concepts for human spaceflight often involve slow, rotating habitats for artificial gravity during long coasting phases, not the sleek, agile fighters of Star Wars. The idea of a boost or a jump to light speed is a narrative shortcut that completely bypasses this physiological reality. In the end, the dream of fast spaceships is crushed not only by the laws of physics, but by the very nature of our own biology. We are soft, squishy, and incredibly vulnerable to rapid changes in motion. The universe may allow for incredible speeds, but our bodies forbid us from reaching them in any meaningful way. This G-force barrier is perhaps the most intimate and humbling of all the obstacles we face, reminding us that we are not built for the violent extremes of space travel as portrayed in fiction. Our path to the stars, if it ever happens, will be a slow, patient, and gradual crawl, respecting the delicate balance that keeps us alive. Every time you see a ship in a movie accelerate rapidly, remember that in the real world, the crew would be dead before they even left the solar system. This fundamental truth redirects our efforts towards propulsion systems that provide gentle, sustained thrust, like ion engines or nuclear thermal rockets. But these have their own limitations, such as very low thrust, making them impractical for human missions where time is a factor. The tyranny of G-force is a silent, ever-present limit that shapes every aspect of crewed space exploration, ensuring that our journey to the cosmos will be a marathon, not a sprint. It forces us to rethink not just our technology, but our very conception of what space travel means, prioritizing survival and safety over speed and spectacle. So, while our imaginations soar with visions of galactic empires, the reality is that we are grounded by the same forces that have always governed life on Earth. And that includes the simple, unyielding fact that too much acceleration turns people into pulp. So, we've accepted that to keep our astronauts from turning into jelly, we have to accelerate slowly and gently, perhaps at a comfortable 1G. But this gentle push introduces a whole new nightmare. a mathematical trap that has haunted rocket scientists for over a century and fundamentally dictates why our spaceships can never be the sleek, fast machines of science fiction. This is the tyranny of the rocket equation, a principle formulated by Konstantin Tsiolkovsky, and it reveals a vicious cycle that makes carrying your own fuel the ultimate enemy of speed. The basic idea is simple. For a rocket to move forward, it has to throw something backward. This is Newton's third law in action. That something is propellant, the mass you eject out the back to create thrust. The faster you want to go, the more propellant you need to eject, and the faster you need to eject it. But here is the catch. All that propellant has mass, and that mass is part of the rocket itself at the start. So, to accelerate the rocket and its payload, you also have to accelerate all the fuel you haven't used yet. This creates a spiral of diminishing returns. Adding more fuel to go faster increases the initial mass, which then requires even more fuel to push that heavier load, and so on. The equation isn't linear, it's exponential. This means that the vast majority of a rocket's launch mass isn't the ship or the payload. It's the fuel itself. For a mission to low Earth orbit, the fuel can make up over 90% of the rocket's mass on the launch pad. The actual spacecraft sitting on top is just a tiny fraction. Now, scale this up for interstellar travel. To reach even a fraction of light speed with a spacecraft of any substantial size, the fuel requirements become absurdly, incomprehensibly large. Imagine you want to accelerate a modest-sized ship to half the speed of light. The amount of fuel needed wouldn't just be large. It would be comparable to the mass of entire oceans or even planets. It's like trying to drive a car from New York to Los Angeles, but needing to carry a fuel tank that weighs more than the Earth itself. The rocket equation mathematically guarantees that for high speeds. The fuel mass dwarfs everything else. This is why science fiction starships, which are depicted as relatively compact and agile, are pure fantasy. A real interstellar vessel would be almost entirely fuel tank. A sluggish, mountainous blob of propellant with a tiny habitable module buried somewhere inside. The energy required to accelerate all that fuel is, as we've discussed, prohibitive. But the sheer physical mass makes the concept unworkable from a logistics standpoint. You can't just fill up the tank. The tank would need to be larger than any structure we've ever built. And this is just for a one-way trip. If you want to slow down at your destination, you need to carry even more fuel for the deceleration burn, effectively doubling the problem. You need fuel to accelerate, and then you need more fuel to slow down. And that extra fuel for slowing down makes the initial ship even heavier, requiring yet more fuel for the acceleration phase. It's a nightmare of compounding mass. This is often called the paradox of the rocket, because it seems counterintuitive that wanting to go faster forces you to carry so much stuff that you can barely move. Some advanced propulsion concepts try to sidestep this by increasing the exhaust velocity. The faster you can throw your propellant out the back, the less propellant you need for the same change in speed. This is measured by something called specific impulse. Ion thrusters, for example, have a very high specific impulse. They eject individual ions at tremendous speeds using electric fields. This makes them incredibly fuel efficient. However, they produce an excruciatingly low amount of thrust. The push from an ion engine is so gentle that it would take years for one to accelerate a small probe to a meaningful speed for a human crew. This is utterly impractical. A ship using ion propulsion would take decades just to leave the solar system, and the crew would spend their entire lives in transit without ever reaching an interesting speed. The trade-off is brutal. High thrust with massive fuel requirements. or low thrust with efficient fuel use but impossibly long travel times. There is no magic bullet that gives you both high thrust and high efficiency with current physics. Nuclear thermal rockets offer an improvement over chemical rockets, but they still face the same fundamental mass problem. Even the most speculative concept, matter-antimatter annihilation, which provides the highest possible energy density, doesn't completely escape this trap, while it reduces the fuel mass significantly compared to chemical rockets. The energy requirements we discussed earlier are still astronomical, and you would still need to carry a substantial mass of fuel, which again adds to the overall mass that needs to be accelerated. The rocket equation is unforgiving. It doesn't care how fancy your engine is. If you have to carry your reaction mass, you are subject to its exponential tyranny. This is why concepts that don't carry propellant, like light sails, are so appealing. They use photons from a laser or the sun for thrust, so they don't have to carry fuel. But as we've seen, they are only suitable for tiny, unmanned probes because the thrust is so low. For a manned ship, the laser power required would be planetary in scale, and you still have the problem of slowing down. The fuel paradox is thus a fundamental showstopper for fast interstellar travel. It means that no matter how advanced our materials science or energy production becomes, the simple act of carrying the means of propulsion will always anchor us to slow speeds or impossibly large vehicle sizes. This mathematical reality is why our rockets today are so massive compared to their payload, and why the idea of a compact Millennium Falcon is a physical impossibility. When you see a movie spaceship darting between planets, remember that, in reality, it would be mostly invisible, hidden behind a colossal cloud of fuel that stretches for miles. The rocket equation is a cold, hard law that doesn't bend for our dreams of galactic exploration. It forces us to accept that space is vast not just in distance, but in the energy and mass required to traverse it. Our journey to the stars, if it ever happens, will not be on a fast ship, but on a slow, ponderous vessel that has made peace with the fact that most of itself is just the stuff it burns to move. This underlying principle shapes every aspect of spaceflight design and ensures that the era of fast starships will remain firmly in the realm of imagination. The paradox of fuel is the silent governor of rocket science, a reminder that in space, every action has an equal and opposite reaction, and the cost of that reaction is a burden that grows exponentially with ambition. So, after grappling with the brutal math of the rocket equation and realizing that carrying our own fuel makes high-speed travel a logistical impossibility, it's tempting to look for a loophole, a way to cheat the system entirely. This is where one of the most famous and tantalizing ideas in all of theoretical physics comes into play: the Alcubierre warp drive. You've seen it in Star Trek, where the captain orders warp factor 1 and the stars stretch into streaks. The Alcubierre drive is the closest thing real science has to that concept. But before we get too excited, we need to understand why it's almost certainly a dead end in practical terms. The idea was proposed by physicist Miguel Alcubierre in the 1990s as a solution within Einstein's field equations of general relativity. It doesn't involve accelerating the ship through space in the conventional sense. Instead, it proposes manipulating the fabric of space-time itself. Imagine space as a rubber sheet. The drive would contract the space immediately in front of the ship, pulling the destination closer, and simultaneously expand the space behind it, pushing the starting point farther away. The ship itself would sit inside a flat, undisturbed region of space called a warp bubble, and it would simply surf on this wave of distorted space-time. Since the ship isn't moving through the space inside the bubble, it wouldn't experience acceleration. inertia, or time dilation effects, it could, in theory, appear to travel faster than light without violating relativity locally because the space around it is moving, not the ship itself. This is a brilliant piece of mathematical gymnastics, and it's perfectly consistent with the known laws of physics on paper. But this is where the fantasy collides with hard reality. For this warp bubble to form and sustain itself, the equations demand the existence of something called exotic matter. This isn't just rare or unknown matter. It's matter with a negative energy density, normal matter. Everything we've ever seen or touched has positive energy density. It gravitationally attracts. Exotic matter would have to have negative energy, meaning it would gravitationally repel. It would be stuff that pushes space apart rather than pulling it together. While certain quantum effects, like the Casimir effect, show that negative energy densities can exist in microscopic amounts for fleeting moments, the existence of stable, macroscopic quantities of exotic matter is entirely hypothetical. There is zero evidence that it exists in a form we could harvest or create. In fact, most physicists believe it probably doesn't exist at all because stable exotic matter could lead to all sorts of paradoxes, like time travel and violations of causality. So, the very foundation of the Alcubierre drive is built on a substance that might be purely imaginary. Let's assume for a moment that we somehow magically found a bucket of this exotic matter. The next problem is the sheer, mind-boggling amount of energy required to power the warp drive. Early calculations suggested you would need energy equivalent to converting the mass of Jupiter into pure energy, just to warp space for a small ship. More recent studies have refined this, suggesting you might only need the mass energy of something like the Voyager probe. But that still requires negative energy densities of a magnitude we can't even conceive of producing. We're talking about energies that dwarf the total output of the Sun for centuries. The infrastructure to generate and control that much energy, especially in the form of negative energy, is so far beyond our capabilities that it's not even a question of engineering. It's a question of whether the universe allows it. Furthermore, there are serious stability and safety issues. The warp bubble would be incredibly fragile. Any minor fluctuation or imperfection could cause it to collapse catastrophically. Even if we could create it, we might not be able to control it. Then there's the problem of the accumulation of particles. As the warp bubble moves through space, it wouldn't just be passing through empty vacuum. It would sweep up interstellar particles and cosmic radiation, trapping them within the bubble. During the journey, these particles would be accelerated to incredibly high energies. When the ship arrives at its destination and the warp bubble dissipates, all this accumulated high-energy material would be released in a massive, directional blast. It would be like firing a cannonball of intense radiation and particles directly at your target planet. The arrival of a warp ship could inadvertently sterilize the entire world it was trying to visit, making the journey pointless and incredibly destructive. This isn't a minor side effect. It's a fundamental consequence of how the drive interacts with the environment. Another huge problem is that we have no idea how to actually create or control a warp bubble. The mathematics describes what could be, but not how to do it. We don't have a warp field generator. We don't know what materials or technology could possibly manipulate space-time in such a precise and powerful way. It's like having a blueprint for a time machine without any clue what the parts are made of or how to assemble them. The Alcubierre drive also faces causality issues. If faster-than-light travel is possible, even through warping space, it could potentially lead to time travel and paradoxes, like going back in time and preventing your own birth. Most physicists take this as a strong hint that nature forbids such possibilities. and the Alcubierre drive might be mathematically possible but physically forbidden by deeper laws of quantum gravity that we don't yet fully understand. So, while the Alcubierre warp drive is a fascinating thought experiment that shows the creativity of theoretical physics, it's not a viable path to fast starships. It essentially trades one set of impossible problems, the infinite energy and mass requirements for acceleration, for another set of impossible problems, the need for exotic matter, astronomical energy, and dealing with catastrophic quantum effects. It's a classic case of kicking the can down the road. The problems it introduces are arguably even more profound and insurmountable than the ones it tries to solve. This is why, despite the popular excitement around the idea, the scientific community remains highly skeptical. Research continues, of course, because exploring the edges of our knowledge is valuable. But no serious scientist is betting on a warp drive being built in the foreseeable future, if ever. It serves more as a tool for understanding general relativity better than a practical engineering goal. When you see a ship warping away in a movie, remember that the real-world version would require magic matter, the energy of a star, and would likely blow up everything at its destination. The dream of bending space to our will remains just that, a dream, and it reinforces the idea that the universe has set firm boundaries for travel. The speed of light isn't just a barrier, it's a fundamental part of cosmic architecture that doesn't yield to clever tricks. Our future in space will have to be built on technologies that work within these limits, not on speculative fantasies that require rewriting the laws of physics as we know them. The Alcubierre drive is a beautiful idea, but it's ultimately a mirage, showing us a cool-looking oasis that vanishes the closer we get. It's a testament to human imagination, but also a reminder that the universe operates on rules that are often harsh and unyielding. So, while we can enjoy the concept in science fiction, for real-world space travel, we need to focus on what's actually possible, even if it's slower and less glamorous. The warp drive is a brilliant piece of math, but it's not a ticket to the stars. Having seen how the Alcubierre drive swaps one set of impossible problems for another, let's examine another popular science fiction trope, the idea of hyperspace or subspace. When a captain orders a jump to hyperspace, the ship doesn't accelerate through normal space. It vanishes into a different dimension where the rules are more forgiving, allowing it to bypass the light barrier entirely and reappear light years away in an instant. This is a wonderfully convenient plot device, but it has absolutely no basis in our current understanding of physics. There is no scientific theory or experimental evidence that suggests such alternate dimensions, where the laws of physics are different and faster than light travel is permitted, actually exist. Concepts like hyperspace are essentially metaphorical shortcuts. They are narrative tools, not engineering concepts. In our universe, as far as we can observe and measure, the laws of physics are consistent. Gravity, electromagnetism, and the nuclear forces work the same way in a galaxy a billion light years away as they do here on Earth. The idea that we could simply slip into a parallel realm where these fundamental constants are different is pure speculation, a modern-day equivalent of sailing off the edge of the world. Even in advanced theoretical physics, such as string theory, which posits the existence of extra dimensions, these dimensions are curled up at an infinitesimally small scale, far smaller than an atom. They are not vast, navigable realms that you can fly a spaceship through. They are mathematical constructs that influence the properties of particles, not highways for travel. Accessing these theoretical dimensions, if they even exist, would require energies trillions of times beyond what the Large Hadron Collider can produce, effectively making it impossible. Furthermore, The act of tearing a hole in the fabric of space-time to enter this hypothetical hyperspace would be an event of cataclysmic energy. The gravitational forces required to rip open a stable portal would be akin to those of a black hole, and the energy input would be unimaginable, likely requiring the mass energy of multiple stars. This isn't just difficult, it's a project that would dwarf the scale of any civilization. And then there's the question of what's on the other side. If you could open a doorway to a realm with different physical laws, the consequences would be completely unpredictable. The very atoms that make up your ship and your body might not hold together. The forces that bind matter might not function. You could instantly disintegrate. Or the universe inside might be a chaotic soup of energy where concepts like direction and destination are meaningless. Navigating such a realm would be impossible because our entire understanding of navigation is based on the consistent laws of our own universe. Without a map, and there can be no map of a place with unknown physics, any journey would be a blind leap into an infinite abyss. This is why hyperspace is a narrative device, not a scientific one. It serves as a metaphor for taking a shortcut. But confusing this metaphor with a physical possibility is a common mistake. Science fiction authors use it because it's elegant and avoids the messy complications of relativity. But in reality, there is no other space to jump into. The space we have is the only space we get. The vacuum of space isn't hiding a secret, vast a lane underneath it. It is the arena in which all physics plays out. The concept also runs into the same causality problems as warp drives. If you can travel from point A to point B almost instantaneously by taking a hyperspace shortcut, you could, from certain reference frames, arrive before you left, creating paradoxes that violate cause and effect. Most physicists believe the universe inherently prevents such paradoxes, which is another strong argument against the physical possibility of hyperspace travel. The silence of the universe. The fact that we haven't seen any evidence of other civilizations using such technology further suggests that it might not be possible. If hyperspace were a viable method of travel, the galaxy would be teeming with traffic, and we would likely see some evidence of these dimensional ruptures or the energy signatures required to create them. We see none of that. The cosmos is quiet, implying that the great filter preventing interstellar empires is, simply, the immutable laws of physics. So, while the idea of flipping a switch and entering a dimension where stars are just a stone's throw away is incredibly appealing, it remains firmly in the realm of imagination. It's a powerful story element, but it has no grounding in reality. Our exploration of the cosmos will be confined to the normal, four-dimensional space-time we call home, with its strict speed limit and vast, empty distances. This doesn't make the universe any less wonderful, it just makes it real. The challenge of space travel is not about finding a magical way to circumvent the rules, but about learning to operate within them. This means accepting long travel times, generation ships, and robotic probes as the most plausible paths forward. The dream of hyperspace is a beautiful one, but it's a dream that distracts from the actual, achievable, though difficult, future of space exploration. It's a cosmic mirage, promising an easy way out that simply doesn't exist. The real adventure lies in confronting the universe on its own terms, with patience, ingenuity, and a respect for the fundamental laws that govern everything. So, the next time you see a ship leap into hyperspace, enjoy the spectacle, but remember that the true frontier is right here, in this dimension, waiting for us to explore it the hard way. Watching ships in science fiction perform breathtaking maneuvers, banking and turning at thousands of kilometers per hour as if they were fighter jets in an atmosphere, is a thrilling spectacle. but this spectacle relies on a piece of technology that is every bit as magical as a hyperspace jump: the inertial dampener. In reality, the physics of inertia make such acrobatics a death sentence for any organic crew, and this is a problem that no amount of engine power can solve. Inertia is a fundamental property of matter, described by Newton's first law. An object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. This isn't just a suggestion, it's a fundamental rule of the universe. What this means for a spaceship is that if it is moving in a straight line at a high speed, everything inside it is also moving at that same speed. If the ship suddenly turns, the crew and all the loose objects inside will continue moving in the original direction until they are stopped by something, usually the ship's wall, cockpit, or console, without a force to change their motion along with the ship. They become projectiles. Imagine a bus driving at 100 kilometers per hour down a highway. If the driver suddenly swerves into a sharp right turn, the passengers are thrown violently to the left. Now, scale that up to a spaceship moving at thousands or even millions of kilometers per hour. A sharp turn would not just throw people against the wall, it would smear them across it with force equivalent to a high-speed car crash. The G-forces involved would be astronomical, crushing bones and pulping organs instantly. This is why the dramatic dogfights seen in movies, with ships weaving through asteroid fields, are physically impossible for manned vessels. The human body simply cannot withstand those lateral accelerations. Fighter pilots on Earth experience high G-forces during tight turns, but they are trained and equipped with special suits to handle forces up to about 9 Gs for short periods. That's 9 times the force of gravity. The maneuvers in sci-fi films would involve hundreds or thousands of Gs, a level of force that would turn a human into a bag of liquid. So, how do we get around this? Science fiction invents the inertial dampener, a device that somehow cancels out the effects of inertia inside the ship, allowing the crew to remain comfortably in their seats regardless of the ship's motion. But what would it actually take to cancel inertia? Inertia is intimately tied to mass. The more mass an object has, the more inertia it has, and the harder it is to change its motion. To cancel inertia, you would need to somehow negate mass, at least locally inside the ship. This brings us to the Higgs field, a fundamental field in the universe that gives elementary particles their mass. Manipulating the Higgs field to remove mass from objects is a technology so far beyond our current understanding that it is purely speculative. We have no idea if it's even possible, and if it were, the energy requirements would likely be prohibitive. Furthermore, if you could cancel an object's mass, you would also be cancelling its weight, and it would behave in strange ways. Without mass, the crew would be weightless and would not be held in their seats by gravity anyway. They would float around. The inertial dampener is therefore a contradictory concept. It needs to cancel inertia to prevent people from being crushed, but it also needs to maintain some form of artificial gravity to keep them in their seats. This is a paradox that has no clear solution in physics. Without such a magical device, the limitations on spacecraft maneuverability are severe. A realistic starship would not be able to make sharp turns at high speed. Its course changes would have to be very gradual, calculated over long distances to keep the acceleration forces on the crew below 1 G, or at most a few Gs for short, emergency maneuvers. This means that space battles would not look like World War II dogfights. They would be more like slow, strategic games of chess played over vast distances, with ships firing at each other from hundreds of thousands of kilometers away. The idea of evading laser fire or plasma bolts by quickly dodging is nonsensical. At the speeds involved, the projectiles would travel the distance almost instantly, and the ship simply couldn't move out of the way fast enough without killing everyone on board. This also affects how a ship accelerates. As we discussed earlier, rapid acceleration is fatal, but even gradual acceleration has to be carefully managed in terms of direction. A ship couldn't just stop on a dime. To slow down, it would have to turn around and fire its engines in the opposite direction for the same amount of time it spent accelerating, a process that takes months or years for interstellar journeys. There is no quick reversal. The need for slow, gentle maneuvers also puts a damper on the idea of landing on planets. A massive starship couldn't descend vertically into a gravity well like a helicopter. The forces required to hover would be immense, and any sudden adjustments could be catastrophic. Realistic planetary landing would likely involve delicate orbital insertion and the use of smaller, specialized shuttles. The problem of inertia is thus a double lock on fast space travel. It prevents rapid acceleration in a straight line, and it prevents rapid changes in direction. This means that even if we solved the energy problem and could travel at near light speeds, we would be stuck flying in nearly straight lines, unable to perform the exciting maneuvers we see on screen. The universe, it seems, is designed for slow, deliberate travel. The absence of an inertial dampener is one of the most overlooked but absolute barriers to the kind of space opera we enjoy in films and TV. It grounds our dreams of agile starships in the harsh reality of Newton's laws. Every time you see a ship in a movie make a sharp turn, remember that in reality, the crew would be a red stain on the bulkhead. This fundamental limitation forces us to conceive of space travel as a peaceful, patient endeavour, not a violent, acrobatic one. It shapes the very design of spacecraft, favouring long, cylindrical designs that accelerate in one direction, with the crew positioned so that the acceleration force feels like gravity. It means that the inside of a realistic starship would look more like a skyscraper than a naval vessel, with decks perpendicular to the direction of thrust. The dream of zipping through space in a nimble fighter is just that, a dream shattered by the unyielding law of inertia. So, while we can enjoy the spectacle of cinematic space battles, we must recognise that they are a fantasy, a violation of physics as fundamental as ignoring gravity. The real frontier of space is quiet, slow, and demands a profound respect for the forces that govern motion. Our journey to the stars will be a graceful, linear ballet, not a frantic dogfight. The unyielding nature of inertia forces us to rely on engines that push against something, but this leads us to a deeper, more fundamental law that governs all motion in the universe, the conservation of momentum. This principle is the ultimate reason why the dream of a reactionless drive, an engine that propels a ship without ejecting any propellant, is almost certainly an impossibility. Every propulsion system ever conceived, from a rowboat to an ion thruster, is based on Sir Isaac Newton's third law. For every action, there is an equal and opposite reaction. To move forward, you must push something backward. In a rowboat, you push water backward with your oars. In a car, you push the road backward with your tyres. In a rocket, you push hot gas backward through a nozzle. The forward momentum you gain is exactly equal to the backward momentum you impart to the exhaust. This is not just a good idea, it's a law of the universe that has been verified countless times. Without something to push against, you cannot create net momentum. In the vacuum of space, there is no air or water to push against, so a rocket must carry its own reaction mass, the propellant it ejects. This is the core of the rocket equation and its tyrannical math. The idea of a reactionless drive is seductive because it promises to break this cycle. Imagine an engine that just moves the ship without spewing anything out the back. It would be the ultimate propulsion system, needing no fuel, facing no rocket equation. and allowing for incredible speeds. Concepts like the EM drive have periodically made headlines, claiming to produce thrust without exhaust. But these claims, upon rigorous investigation, always run into the same fundamental problem. They appear to violate the conservation of momentum. If a device inside a closed box could make the box move without interacting with anything outside, it would be creating momentum from nothing. This is equivalent to sitting inside a car and pushing on the dashboard to make the car move. It simply doesn't work because the forces are internal and cancel out. The conservation of momentum is a bedrock principle of both classical and quantum physics. It is tied to the fact that the laws of physics are the same everywhere in space. This symmetry is what guarantees momentum is conserved. To violate conservation of momentum would be to rewrite the most fundamental tenets of our understanding of the universe. So, when we hear about a reactionless drive, the burden of proof is extraordinarily high, in every case so far. When such devices are tested in carefully controlled experiments, the measured thrust either disappears or is explained by external effects, such as thermal expansion, magnetic interactions with the Earth's field, or measurement errors. The EM drive, for instance, when tested in a vacuum with proper controls, showed no anomalous thrust. The few positive results were likely due to experimental artifacts. This is not to say that scientists are closed-minded. They are rightfully skeptical because the claim contradicts a foundation of physics. If a reactionless drive were possible, it would not just revolutionize space travel. It would overturn centuries of established science. It would mean that our understanding of everything from the motion of planets to the collision of subatomic particles is fundamentally wrong. That is a monumental claim, and it requires monumental evidence, which so far does not exist. So, what are our realistic options? We have systems that don't carry chemical fuel, but they still eject reaction mass, ion thrusters. For example, use electricity to accelerate ions to extremely high speeds. They are very efficient, meaning they get a lot of push for a little bit of propellant, but they still require propellant and they still obey Newton's third law. Solar sails use photons from the sun for thrust. Photons have momentum, and when they reflect off the sail, they impart that momentum to the spacecraft. This is a truly fuel-free propulsion system in the sense that it doesn't carry its own propellant, but it still relies on ejecting something, in this case, dot. It's pushing against the incoming stream of photons. It doesn't violate conservation of momentum. It uses momentum from the sun. The problem is that the thrust from a solar sail is incredibly weak, suitable only for slow, patient journeys across the inner solar system, for interstellar travel. We might use giant laser sails, where a powerful laser beam from Earth pushes on the sail. But again, this is not reactionless. The laser is pushing the spacecraft, and the momentum comes from the laser installation. The spacecraft is still interacting with an external force. Even the most exotic theoretical concepts, like the Alcubierre drive, do not violate conservation of momentum within the bubble. They shift the problem to warping space-time itself, which still involves energy and momentum conservation on a cosmological scale. The takeaway is stark. There is no free lunch in propulsion. You cannot get something for nothing. To move, you must exchange momentum with something else. This fundamental law acts as a universal speed governor. It means that the performance of any real propulsion system is always limited by the mass of propellant it can carry and the speed at which it can eject that propellant. This is why the compact, agile starships of science fiction are impossible. Their engines, as depicted, are reactionless. They glow and make noise, but they don't show a massive, continuous exhaust stream being ejected at relativistic speeds. A real engine capable of accelerating a ship to a significant fraction of light speed would produce an exhaust beam so energetic it would vaporize anything behind it for thousands of kilometers. A plume of pure energy visible across the solar system. The conservation of momentum is therefore the silent, non-negotiable rule that underpins the rocket equation, the energy problem, and the sheer impracticality of fast interstellar travel. It forces us to accept that space exploration will be a slow, gradual process, dependent on carrying reaction mass or harnessing external forces like light pressure. It grounds the grandiose dreams of science fiction in the hard, unyielding reality of physics. So, the next time you see a spaceship silently gliding through the void, remember that, in reality, it would be trailing a brilliant, star-hot jet of exhaust, a testament to the fact that in order to go forward, we must always throw something away. This law is not a limitation of our technology. It is a limitation of the universe itself. Our journey to the stars will be a conversation with this law, a negotiation with momentum, and it will be a long, slow, and careful conversation. The dream of an engine that just works without pushing on anything is a fantasy, a violation of a cosmic rule that has been in place since the beginning of time. We are bound by momentum, and that binding is what makes the cosmos both a challenge and a consistent, predictable place to explore. The unbreakable chain of physical laws we have been discussing, from the conservation of momentum to the light speed barrier, leads us to a profound and unsettling question about our place in the cosmos. A question known as the Fermi paradox. If the universe is so vast and ancient, with hundreds of billions of stars in our galaxy alone, many with planets that could potentially harbour life, then where is everybody? The sheer scale and age of the galaxy suggests that if interstellar travel were even remotely feasible, especially the fast kind we see in movies, the universe should be teeming with life and evidence of cosmic engineering. Yet, when we gaze out into the void, we are met with a profound and deafening silence. This silence is not just an absence of radio signals. It is an absence of any detectable artifacts, any megastructures, any signs of cosmic traffic. This paradox, formulated by physicist Enrico Fermi, strongly implies that there are formidable great filters that prevent civilizations from becoming spacefaring entities on a galactic scale. The most compelling and likely candidate for this great filter is not a mysterious external force, but the very laws of physics we have been exploring. The barriers to fast interstellar travel are not merely technological hurdles that a slightly more advanced civilization could overcome. They are fundamental features of the universe itself. The speed of light limit, the astronomical energy costs, the hazards of relativistic travel, and the psychological and sociological challenges of time dilation and generational journeys. These are not problems waiting for an ingenious solution. They are immutable facts of cosmic life. This suggests that no civilization, no matter how intelligent, can ever bypass these limits. The galaxy may be filled with life, but that life is almost certainly planet-locked, isolated on its own world, staring up at the stars just as we do, but unable to reach them in any meaningful, rapid way. The dream of a galactic empire is a fantasy because the physics that would enable its administration and trade, fast travel and communication is forbidden. The silence we hear is the sound of these laws being enforced. It is the sound of a cosmic quarantine. Each world is an island in an ocean that is impossible to cross quickly. This interpretation of the Fermi paradox is both humbling and clarifying. It tells us that the reason we have not been visited is not because life is impossibly rare. but because travel is impossibly difficult, it suggests that the great filter lies not in our past, in the unlikely emergence of life or intelligence, but in our future, in the physical impossibility of becoming a truly interstellar species. The challenges are so profound that they likely represent a permanent ceiling for any technological civilization. We might master our solar system, building habitats around Mars and the moons of Jupiter, but the leap to the stars is of a different order of magnitude entirely. It is a chasm that cannot be bridged with technology because the universe itself defines the width of that chasm. This also resolves the paradox of why we see no evidence of ancient, super-advanced civilizations. If a civilization had arisen 1 billion years ago, surely it would have colonized the entire galaxy by now, right? Not if the speed of light is a hard limit and the energy requirements are prohibitive. Even at a substantial fraction of light speed, colonizing the entire galaxy would take tens of millions of years, a timescale so long that the civilization itself might rise and fall before the project was complete. The incentives for such a slow, grinding, and costly expansion are likely minimal. The economic and logistical burden is so immense that it may never be worth the effort for any society. The absence of alien visitors, therefore, is not a mystery. It is the expected outcome. It is evidence that the physics we have discovered in our laboratories here on Earth applies universally. The laws that prevent us from building fast starships are the same laws that have prevented every other species in the cosmos from doing so. We are not late to the party. The party never started because the venue is fundamentally closed for business. This perspective should reshape our vision of the future. It directs our ambitions inward, toward making the most of our own solar system, rather than dreaming of conquests among the stars. It suggests that our planet, Earth, is not just a cradle but likely our permanent home, and that the stewardship of this world is the most important task we have. The search for extraterrestrial intelligence should continue, but we should not expect to find neighbours we can visit. We should expect to find distant cousins we can only wave to across the immense, silent gulf of space, using the one thing that can travel at the speed of light: information. Our conversations will be slow, measured in years or centuries, a patient exchange of knowledge and culture between isolated islands of life. The Fermi paradox, therefore, is not a warning that we are alone, but a lesson that we are all in the same boat, forever bound by the same physical constraints, forever gazing at the same unreachable stars. The universe is not empty of life. It is full of silent, isolated gardens, each one beautiful and unique, but forever separated by deserts of space and time that cannot be crossed. This is the ultimate reason why we will never have starships as fast as those in the movies. Because if it were possible, the sky would already be full of them, and it is not. The silence is the answer. So, after contemplating the profound silence of the cosmos and the Fermi paradox, we are left with the realization that the universe seems to impose a permanent speed limit. But even if we could somehow circumvent all those previous barriers, there is another brutally practical and often overlooked problem that would stop a starship dead in its tracks: heat. Imagine building the most powerful engine imaginable, one that can harness the energy of stars to propel a ship at relativistic speeds. Now, imagine that engine, and every other system on board, generating waste heat as an unavoidable byproduct. In the void of space, there is no air to carry that heat away through convection or conduction. The only way to get rid of it is by radiating it away as infrared light. This turns your majestic starship into a flying oven, and managing that heat becomes an engineering nightmare of astronomical proportions. Every single process that uses energy, from the main thrusters to the life support systems to the computers, produces heat. Inefficiencies in energy conversion mean that a significant portion of the immense power required for interstellar travel would be wasted as heat. For a ship accelerating to a fraction of light speed, the power consumption would be comparable to that of a small planet, and thus the heat generated would be equally colossal. If you cannot dissipate this heat, the interior temperature would rise rapidly, cooking the crew, melting electronics, and ultimately causing a catastrophic failure. The ship would essentially self-destruct from within long before it reached its destination. To understand the scale, think about your laptop when it runs intensive tasks. It gets hot and needs a fan to blow air over its components to cool it down. In space, there is no air, so you rely solely on radiators, which are special surfaces designed to emit thermal radiation. The effectiveness of a radiator depends on its surface area and temperature. The hotter it is, the more heat it radiates per square metre. But there is a catch. You cannot make the radiators arbitrarily hot because that could damage them or pose a risk to the ship. So, for a given radiator temperature, you need a massive surface area to radiate away the heat. For a starship with a power output equivalent to all of human civilization, the radiator area required would be enormous, potentially covering square kilometers. This adds tremendous mass and complexity to the spacecraft, which in turn requires more energy to accelerate, exacerbating the very problem you are trying to solve. It is a vicious cycle. Moreover, these radiators would be incredibly vulnerable. They are large, thin, and delicate structures that could be easily damaged by micrometeoroids or debris, and if they fail, the ship quickly overheats. In a combat scenario, as often depicted in movies, targeting the radiators would be a surefire way to disable an enemy vessel. But even in peaceful travel, the radiators pose a design challenge. They must be deployed away from the main hull to avoid heating the ship itself, and they might need to be retracted during high acceleration or maneuvers, which limits their effectiveness when the heat generation is at its peak. Now, consider the infrared signature. A ship glowing with waste heat would be visible across light years as a bright beacon in the infrared spectrum. Any hope of stealth in space is utterly impossible because you cannot hide the heat you are radiating. You would be announcing your presence to the entire galaxy, which might not be desirable. This heat radiation is not just a side effect. It is a fundamental limit on the power density of any spacecraft. The more power you use, the more heat you must reject, and eventually, you hit a point where the radiators become impractically large and heavy. This is why real-world spacecraft, like the International Space Station, have extensive thermal control systems with large radiator panels, and even then, they are dealing with mere kilowatts of power. An interstellar starship would be dealing with petawatts or exawatts, a scale difference of many orders of magnitude. The heat problem also affects the propulsion system directly. For example, in a nuclear thermal rocket, the reactor core must be kept cool, which requires pumping coolant through it, and that heat must then be radiated away. In an ideal matter-antimatter engine, the annihilation produces immense heat that must be managed. Even the theoretical Alcubierre warp drive would generate heat from the equipment needed to create and sustain the warp bubble. There is no free pass. Every advanced propulsion concept must account for thermal management. Furthermore, the internal heat from the crew and equipment adds to the burden. Humans generate about 100 watts of heat each just from metabolism, and all the computers, lighting, and machinery contribute more. For a long-duration mission with a large crew, this becomes significant. Without effective cooling, the living quarters would become uninhabitable. This is why generation ships or any long-term habitat must have robust and redundant thermal control systems. The failure of such a system would mean a slow, gruesome death for everyone on board. In summary, the challenge of heat dissipation is a showstopper that is often glossed over in science fiction. While energy and propulsion get the spotlight, the humble radiator is the unsung hero that determines whether a mission is feasible. The laws of thermodynamics are inexorable. You cannot create energy without waste heat, and you cannot get rid of that heat without large, massive, and vulnerable radiators. This adds another layer of impossibility to the dream of fast starships. Even if we solved the light barrier, the energy crisis, and the hazards of relativistic travel, we would still be left with a ship that either melts from its own power or is so burdened by radiators that it can barely move. The universe, it seems, has multiple locks on the door to the stars, and heat dissipation is one of the sturdiest. It forces us to acknowledge that space travel is not just about going fast. It is about managing the basic physical consequences of using immense power in an environment that is ruthlessly efficient at trapping heat. So, the next time you see a sleek spaceship zooming across the screen, remember that, in reality, it would be trailing gigantic, glowing radiators, a testament to the fact that in space, you cannot just overpower physics, you must learn to live with its constraints. And heat is one of the most demanding of them all. This realization should guide our future efforts toward more efficient and sustainable technologies, perhaps even reconsidering the very need for speed, and instead focusing on patience and endurance as our allies in the cosmic ocean. The flying oven is not just a metaphor, it is a physical reality that cools our ambitions as surely as it heats our spacecraft. Faced with the relentless accumulation of these physical showstoppers, from heat management to energy requirements, we are forced to abandon the science fiction dream entirely and confront the only two realistic forms of interstellar exploration that remain on the table. These are not the sleek, fast starships of popular culture, but two profoundly different and challenging concepts: the generation ship and the robotic probe. Both represent a fundamental acceptance of the universe's harsh terms, trading speed for survival and immediacy for patience. The generation ship is the ultimate expression of long-term thinking. It is not a vessel designed for a quick round trip. It is a moving city, a self-contained ecosystem intended to sustain multiple generations of humans during a voyage that could last centuries or even millennia. The ship would be colossal, a rotating cylinder or ring to simulate gravity through centrifugal force, containing farms, water recycling systems, and a society that must remain stable and purposeful across hundreds of years. The crew that departs from Earth would not be the one that arrives at the destination. Their children, or their children's children, would be the ones to finally see another star system. This introduces a host of staggering challenges beyond mere engineering. Could a society remain cohesive and motivated for such an immense duration? What cultural and linguistic drift would occur over the centuries? How would they maintain the knowledge and skills necessary to operate the ship and complete the mission upon arrival? The psychological and sociological hurdles are as daunting as the physical ones. The ship would be a fragile, closed system, vulnerable to disease, societal collapse, or technological failure over the long term. A single crop blight or a major systems malfunction could doom the entire mission. Furthermore, the people born on the ship would have no connection to Earth. It would be a mythical place in their history. They would be born into a journey they did not choose, with the sole purpose of one day reaching a world they have never seen. This raises profound ethical questions about committing countless generations to a life in metal halls for a goal that may not even be relevant by the time they arrive. The alternative, and in many ways the more scientifically plausible option, is to forego human crews altogether and send robotic probes. These would be highly advanced, autonomous machines, perhaps no larger than a shoebox, equipped with sophisticated AI and a suite of scientific instruments, without the need for life support, radiation shielding for fragile biology, or vast living spaces. These probes could be designed for sheer endurance and efficiency. They could be propelled by methods that are impractical for human travel, such as light sails pushed by giant lasers. This could accelerate them to a significant fraction of light speed, perhaps 20 or 30%, making the journey to nearby stars a matter of decades instead of centuries. The Breakthrough Starshot initiative is a real-world example of this thinking, aiming to send tiny probes to Alpha Centauri within a single human lifetime. However, this approach has its own deep limitations. The primary one is the sheer difficulty of building a fully autonomous system that can operate flawlessly for decades in a hostile environment, navigate unknown space, and conduct complex scientific operations upon arrival without any direct human control. The communication lag alone would be immense. It would take years for a signal from the probe to reach Earth, and years more for any commands to be sent back. The probe would have to be incredibly smart and independent. Furthermore, while these probes could send back invaluable data, they would not fulfill the human desire to set foot on another world. They are explorers in the purest sense, but they are not colonists. They extend our senses, but not our presence. The information they return would be priceless, but it would be a picture, not an experience. This dichotomy between generation ships and robotic probes defines the actual frontier of interstellar travel. One is a monumental sociological experiment that carries our biology but sacrifices individual lives to the journey. The other is a technological marvel that extends our reach but leaves our bodies behind. Both are a universe away from the Star Trek model of exploration. They are slow, patient, and humble. They accept that the stars are not nearby destinations but distant milestones, reachable only through immense sacrifice or through the patient extension of our machinery. The generation ship is a testament to human endurance and long-term planning, while the robotic probe is a testament to our ingenuity and our ability to project our curiosity beyond the limits of our flesh. One requires us to become a spacefaring civilization in the truest sense, living our entire lives between stars. The other requires us to become master engineers and programmers, creating artificial emissaries to be our eyes and ears. Neither is easy, and both are fraught with risk. But these are the only paths that remain when we subtract fantasy from physics. The dream of a quick hop to another star system is a comforting illusion, but the reality is a choice between a multi-generational arc or a one-way message in a bottle thrown into the cosmic ocean. This is the sobering, yet strangely inspiring, truth of our cosmic situation. We are not destined for a galaxy of fast starships and galactic empires. We are destined for a galaxy of slow, patient journeys, either of our bodies or our machines. Our legacy among the stars may not be flags and footprints, but data streams and generations of humans who know only the inside of a ship. It is a future that requires a different kind of courage, not the courage of the pioneer setting out for a new life, but the courage of the architect planning a city that they will never see completed, or the courage of the programmer writing code for a mission that will outlive them. This is the real future of space exploration, and it is both more challenging and more profound than any science fiction fantasy. The sheer scale of a generation ship or a massive probe mission forces us to confront the most grounded, yet perhaps most insurmountable, barrier of all, the economics. Building an interstellar ark is not a project for a corporation or a single superpower. It is an endeavour that would demand the total mobilization of our entire global civilization for centuries. An undertaking so vast it makes every human achievement in history look like a small-scale project. The cost in resources would be astronomical, and I mean that literally. We are not talking about a few $1 trillion. We are talking about diverting a significant fraction of our planet's industrial and economic output for dozens of generations. First, consider the material requirements. The ship itself would need to be a self-sustaining world, likely kilometers long, constructed from millions of tons of advanced alloys, composites, and shielding materials. Where do we get all this metal? Earth's resources are finite and already strained. We would likely have to become a true spacefaring civilization just to gather the raw materials, mining asteroids and perhaps even the moon to avoid completely stripping our own planet. This requires a massive space-based infrastructure that we do not currently possess. Refineries in orbit, zero-G manufacturing facilities, and a fleet of cargo spacecraft far larger than anything we have today. The energy required for this construction phase alone would dwarf our current global energy consumption. Then there is the propulsion system. Whether it is a massive fusion drive or some other advanced technology, building an engine capable of accelerating such a behemoth for years on end is a project that would consume the efforts of the world's best engineers and scientists for a century. The research and development costs are incalculable. You could not just decide to build it. You would have to decide to fundamentally reorient human society toward this single, distant goal. This means centuries of focused effort, where a significant portion of our economic productivity is funneled into a project that offers no immediate return on investment. There is no profit motive strong enough to justify this. No corporation has a planning horizon of 1,000 years. No government can promise its taxpayers that their great-great-great-grandchildren might see the launch. The economic payoff is essentially zero. What would the ship trade? What resources could it possibly bring back that would justify the initial investment? There is no business case for interstellar travel. This makes it a purely philosophical or exploratory endeavour, the kind that only a stable, unified, and incredibly prosperous global civilization could even consider. It would be a modern-day pyramid building, but on a cosmic scale, where the entire planet works for generations to entomb a few thousand people in a metal tomb heading for the stars. The political and social challenges are equally daunting. Could humanity ever achieve the level of long-term global cooperation required? Would nations agree to sacrifice their short-term prosperity for a goal so distant? History suggests we struggle with cooperation even on existential threats that are immediate and obvious. An interstellar ship is the opposite. It is a distant, abstract dream. The project would be incredibly vulnerable to shifts in political will. A war, an economic depression, or a change in leadership could defund and cancel the project a century into construction, wasting all the accumulated effort. Furthermore, the opportunity cost is staggering. The resources poured into a generation ship could instead be used to solve problems here on Earth, ending poverty, curing diseases, transitioning to clean energy, or adapting to climate change. From a purely utilitarian perspective, it is difficult to justify spending the wealth of a planet to send a tiny fraction of its population on a one-way trip when that same wealth could improve the lives of billions who remain. This economic reality is why science fiction glosses over it. It is narratively boring. It is more exciting to show a starship being built in a year in a secret shipyard than to contemplate the millennia of social and economic effort required. The truth is that the economy of a starship is a paradox. To have the kind of surplus wealth and technological capability to build one, we would need to be a Type 1 civilization on the Kardashev scale, masters of our planet's energy. But once we achieve that, would we still have the reckless, expansionist drive to leave, or would we be content in a comfortable, managed planetary society? The economic barrier may be the final and most human of all the filters. It is not a law of physics, but a law of human nature and social organization. We are simply not built, economically or politically, for projects of such staggering scale and patience. Our economic systems are based on short-term growth and quick returns. Our political systems are based on election cycles that last a few years. An interstellar ship requires the opposite, long-term vision and stability beyond anything we have ever achieved. Therefore, the existence of a fleet of fast starships, as depicted in movies, implies not just a solved physics problem, but a solved economics and sociology problem. It implies a civilization that has transcended scarcity, petty nationalism, and short-term thinking. We are nowhere near that. So, while we can dream of the engineering, we must also dream of an economic revolution, a new way of organizing ourselves as a species, before the first rivet on the first interstellar ship is ever put in place. The price of the stars is not just energy, it is our entire focus as a civilization for 1,000 years. That may be the most expensive price tag of all. So, after wrestling with the astronomical economics and societal hurdles of building an interstellar ark, you might think that actually piloting such a vessel would be the straightforward part, a serene journey through a star-dusted void. But the universe has one more perceptual trick up its sleeve, an effect that would utterly transform the navigator's view into something unrecognizable and dangerously alien. This is the relativistic Doppler effect, and it guarantees that the iconic view of streaking stars from a science fiction cockpit is a complete fantasy. In reality, as your ship approaches a significant fraction of light speed, the cosmos outside your window would not stretch into brilliant lines. It would instead collapse into a tunnel of oppressive darkness punctuated by lethal radiation. To understand why, we need to recall what the Doppler effect is. You experience it every day when an ambulance drives past you. The sound pitch is higher as it approaches and lower as it recedes. Light behaves in a similar way, but with relativity factored in, the consequences become extreme. When you move towards a source of light, you effectively catch up with the light waves, compressing them and shifting them towards the blue end of the spectrum. When you move away, you stretch the waves, shifting them towards the red end at everyday speeds. This is negligible, but at relativistic velocities, it dominates your entire visual field. Imagine you are accelerating towards a distant star. The light from that star, which is normally in the visible spectrum, starts to blue shift. As you go faster, it shifts through blue, into ultraviolet, and then into X-rays, and finally gamma rays. The entire constellation of stars in front of you would no longer be a collection of friendly, twinkling points of light. They would become a concentrated, forward-facing wall of invisible, high-energy gamma radiation. This isn't just a visual change, it is an existential threat. Gamma rays are ionizing radiation, capable of penetrating most shielding and damaging DNA, causing cancer and radiation sickness. Your ship's hull would need to be absurdly thick to protect against this constant, directional barrage, adding yet more mass to your already overburdened spacecraft. Meanwhile, The light from the stars you are leaving behind undergoes the opposite transformation. It redshifts, sliding down the spectrum from visible light to infrared, then to microwaves, and finally into radio waves. To your eyes, the stars astern would simply fade away and vanish, leaving behind a profound blackness. So, looking forward, you see nothing but a potential death ray of invisible energy. Looking backward, you see an empty, receding darkness. The spectacular vista of the Milky Way would be gone, replaced by a small, bright, and deadly spot directly ahead, the destination star and nothing else. The romantic notion of watching the universe stream past your viewport is dead. You are flying blind through a tunnel, with only instruments to guide you. This also shatters another sci-fi trope, the view of elongated stars. Some films show stars stretching into lines due to the speed. This is based on a real phenomenon called stellar aberration, where the apparent position of stars shifts slightly, but at relativistic speeds. The Doppler effect is so overpowering that the color shift and intensity changes would make any such stretching irrelevant to human vision. The light simply wouldn't be in the visible spectrum anymore. Furthermore, the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space, would also be Doppler shifted. From your perspective, it would blue shift into a intense, forward-facing cone of microwave or even infrared radiation, adding to the heat load and radiation danger. The universe itself becomes a directional hazard. This has dire implications for navigation. How do you steer when you cannot see? You would be entirely dependent on active sensors like radar and LiDAR, but these too would be affected by relativity. Sending out a radar pulse and waiting for its return becomes complicated when time dilation and length contraction are in play. Your entire spatial awareness would be mediated by computers interpreting distorted data. A small error in calculation could mean missing your target by light years. This sensory deprivation and distortion would also be a psychological burden on the crew. Humans are visual creatures, and being confined to a metal hull with no external visual reference, only instrument readouts showing a universe of invisible dangers, could lead to disorientation, anxiety, and a profound sense of isolation. The journey would become even more claustrophobic and mentally taxing. This effect is not a minor curiosity. It is a fundamental aspect of travelling at relativistic speeds. It means that even if you solved the energy problem, the propulsion problem, the shielding problem, and the economic problem, you would still be confronted with a universe that becomes inherently hostile to perception and navigation at high velocities. The cosmos seems designed to discourage high-speed travel by making it not only difficult and expensive, but also sensorily void and perilous. It is another layer of the universe's keep out sign. This relativistic Doppler effect ensures that the experience of space travel is nothing like what we see in movies. There is no thrilling, visually stunning warp speed effect. There is only a silent, dark, and dangerous sprint through a tunnel where the only visible light is a lethal beacon at the end. This reality forces us to reconsider the very nature of exploration. It suggests that fast travel comes at the cost of disconnection from the visual cosmos. The stars are not there to be enjoyed as a scenic backdrop on a quick trip. They are distant markers that transform into threats when approached too quickly. Therefore, the dream of piloting a fast ship through a galaxy ablaze with light is a sensory illusion. The true face of relativistic travel is darkness and radiation, a journey undertaken on instruments alone, a blind leap through a space that has been rendered invisible and hostile by the very speed required to traverse it. This is perhaps the most poetic and cruel of all the physical barriers. The universe denies us not only the means to travel fast, but also the sight of the journey itself. It tells us that the cosmos, in its infinite wisdom, reserves its beauty for those who are slow enough to see it. So, the next time you see a starship captain gazing at a panoramic view of streaking stars, remember that, in reality, the screen would be black, the crew would be relying on schematics and sensors, and the only light would be a silent, deadly gamma-ray beacon calling them forward into the dark. This final perceptual barrier cements the conclusion that fast spaceships are not just impractical. They are sensory impossibilities, robbing us of the very experience we seek in exploration. The universe, it seems, insists that if we are to visit the stars, we must do so slowly, patiently, and with a deep respect for the light that we are distorting simply by our passage, after confronting the disorienting and hazardous reality of relativistic travel, where the universe itself seems to conspire to blind and irradiate you. It is natural to wonder if there is a smarter way, a backdoor or a shortcut that avoids all these high-speed complications entirely. This is where the concept of wormholes comes in, a staple of science fiction that promises instant travel across the galaxy by stepping through a cosmic tunnel. The idea is incredibly appealing. Why spend centuries travelling the long way when you can just take a shortcut through the fabric of space-time? Unfortunately, while wormholes are a fascinating and mathematically possible idea within Einstein's theory of general relativity, they are almost certainly not the answer to our interstellar travel dreams, and they come with a set of problems that make them even more fantastical and unworkable than simply trying to go fast. A wormhole is theorized as a kind of tunnel or bridge connecting two distant points in space-time. Essentially a shortcut that could reduce a journey of thousands of light years to a mere step. The mathematics allows for such structures. But that is where the good news ends. The first and most immediate problem is stability. The wormholes predicted by the equations are incredibly unstable. They are often described as pinpricks in the fabric of space-time that would snap shut in an instant, far quicker than the blink of an eye, if even a single particle of light, a photon, tried to pass through. Imagine a tunnel made of soap film that collapses the moment you touch it. That is the inherent nature of a basic wormhole. To prevent this instantaneous collapse and keep the tunnel open long enough for anything to traverse it, you would need a very special and utterly hypothetical substance known as exotic matter. Exotic matter is not just rare or unknown. It is matter that possesses negative energy density, meaning it would have to gravitationally repel rather than attract. Normal matter, everything we have ever observed, has positive energy density and pulls things together through gravity. Exotic matter would have to push space apart, acting as a kind of anti-gravity material to prop open the wormhole throat. The problem is, there is no evidence that such matter exists in a stable, macroscopic form. Certain quantum effects, like the Casimir effect, show that negative energy densities can occur in tiny amounts for fleeting moments at the quantum scale. But this is a far cry from having buckets of this stuff to line a traversable wormhole. Most physicists believe that exotic matter, if it can exist at all, is likely prohibited from existing in the quantities needed by some deeper law of physics, because it could lead to violations of causality and paradoxes like time travel. Even if we magically had a supply of exotic matter, the energy requirements to create and stabilize a wormhole large enough for a spaceship are thought to be astronomical, perhaps requiring the mass energy of entire stars or more. The engineering challenges are beyond comprehension. We are talking about manipulating the fundamental geometry of the universe on a macroscopic scale. something we have no idea how to even begin. Furthermore, there is the issue of creating the wormhole in the first place. Do they occur naturally? There is no observational evidence for natural wormholes anywhere in the universe. If they did exist, they would be incredibly rare and likely microscopic. Could we create one artificially? The energy and technology required are so far beyond our capabilities that it is pure speculation. The process might involve concentrating immense gravitational fields, perhaps similar to those of a black hole, but without the event horizon, which is another layer of impossibility. Then there are the hazards of actually travelling through one. Suppose you somehow have a stable wormhole held open by exotic matter. What happens when you try to go through? The journey might not be smooth. The intense gravitational forces and tidal effects near the throat could spaghettify any object, stretching it into a long, thin string of atoms, even if the wormhole is engineered to be safe from such effects. There is a potential quantum danger. As matter travels through the wormhole, it could interact with the exotic matter in unpredictable ways, potentially triggering a quantum instability that causes the wormhole to collapse catastrophically during transit, destroying the ship. Some theories suggest that the mere act of trying to pass through could cause the wormhole to decay into a black hole or simply vanish. Another profound issue is the paradox of time travel. If wormholes allow for faster-than-light travel, even indirectly by shortening the path, they could also allow for travel back in time, depending on how the two ends are moved relative to each other. This opens up all the famous paradoxes, like going back in time and preventing your own birth. Most physicists take this as a strong hint that nature forbids such phenomena, and that traversable wormholes are therefore physically impossible, as they would violate causality. The universe seems to have a built-in mechanism to prevent paradoxes, and wormholes likely fall foul of this. So, while the idea of a wormhole is a beautiful and mind-bending concept that pushes the boundaries of our understanding of general relativity, it is not a practical solution for space travel. It exchanges the immense difficulties of high-speed travel for a set of even more profound and likely insurmountable problems involving exotic matter, astronomical energy, stability, and causality. Wormholes remain in the realm of theoretical physics and science fiction, a tool for exploring the implications of our equations rather than a blueprint for a stargate. They teach us that the universe may not have convenient shortcuts after all, and that the only way to the stars is the long, slow, and patient way, respecting the laws of physics as we know them. The dream of instant travel is seductive, but the reality is that space-time seems to be rigid and unforgiving, designed to keep distances real and travel time-consuming. Therefore, the next time you see a ship vanishing into a shimmering portal, remember that in reality, such a portal would probably collapse, require magic matter, or lead to a timeline with impossible paradoxes. Wormholes are a brilliant theoretical exercise, but they are not a ticket to the stars. The romantic focus of every space opera is the thrilling moment of launch, the powerful leap into the great unknown as the starship accelerates to unimaginable speeds. We are captivated by the raw power needed to break the bonds of gravity and achieve velocity. But this narrative almost completely ignores the other half of the journey, the part that is just as critical and, in many ways, even more demanding: the deceleration. You cannot simply fly a spaceship at a planet or a star system at near light speed and expect to stop on a dime. The forgotten half of the voyage is the one where you have to slow down, and the physics of doing so are a mirror image of the acceleration problem, doubling the nightmare we have already described. Imagine you are on a highway, and you press the accelerator to the floor to get your car up to 200 miles per hour. That requires a certain amount of fuel from your tank. But to bring the car back to a complete stop, you need to use the brakes, which in a spaceship means firing your engines in the opposite direction for an equal amount of time. This braking maneuver consumes just as much fuel as the acceleration did. So, for a simple round trip where you accelerate, coast, and then decelerate at both the destination and back home, you need to carry fuel for 4 major engine burns. Accelerate out, decelerate there, accelerate back, and decelerate home. This simple reality is catastrophic for mission planning. It means that the propellant mass required is not just large, it is exponentially larger than for a one-way trip. The rocket equation, which we know is tyrannical, makes this a vicious cycle. To carry the extra fuel for the return deceleration, you need a bigger ship, which requires more fuel to accelerate that bigger ship, and so on. This is why most realistic interstellar mission concepts are one-way trips. There is no coming back. The energy required to slow down a macroscopic ship from a significant fraction of light speed is, like the energy to accelerate it, astronomical. It is the same colossal amount of energy, just applied in the opposite direction. You are essentially having to build 2 engines into one ship. The one that pushes you forward and the one that pushes you backward to stop. And you have to carry the fuel for both from the very beginning. This is the ultimate logistical trap. Let us consider a probe. For instance, sent to Alpha Centauri. If it accelerates for half the journey, it must decelerate for the second half to enter orbit around the target star. This means it can only use half its total fuel capacity for the initial acceleration, severely limiting its top speed and dramatically increasing the travel time. If it does not carry deceleration fuel, it becomes a flyby mission, screaming through the alien solar system in a matter of hours, with only a fleeting moment to collect data before it is lost forever to the interstellar void. For a flyby probe, this might be acceptable, though scientifically limited. For a human crew, a flyby is pointless. The whole objective is to stop, to explore, to land. A ship that cannot decelerate is a ship on a suicide mission, a tomb hurtling endlessly through the galaxy. This necessity to slow down also complicates any theoretical propulsion system. A laser-powered light sail, for example, is a brilliant concept for acceleration. A giant laser on Earth pushes the sail to high speed. But how does it slow down? There is no giant laser at the destination to push back on the sail. Some concepts suggest using the destination star's light, but this is far too weak for effective deceleration of a massive object. Others propose a complicated maneuver where the sail is detached and used as a mirror to reflect laser light from the home system back onto a separate braking sail. But the precision and timing required for this over light years are mind-boggling. The deceleration problem kills the elegance of many otherwise promising ideas. For a generation ship, the issue is existential. The ship must carry enough fuel to slow its enormous mass at the end of a centuries-long journey. This fuel must be stored, maintained, and kept stable for generations. The systems that will perform the deceleration burn must remain perfectly functional after a millennium of travel. The society on board must retain the knowledge and ability to execute this incredibly complex and critical maneuver, the failure of which would mean flying past their new home into a perpetual, hopeless exile. This doubles the engineering and sociological challenge. Furthermore, the act of deceleration itself would be a dramatic event for the crew. After perhaps centuries of weightless coasting, the main engine would fire again, creating a sense of gravity in the opposite direction. The entire ship would have to be reoriented for a crew that has known only the journey. The final braking phase would be the most perilous part of their entire history. a make or break moment for their entire civilization. In science fiction, this is rarely depicted. The ship just arrives. It slows down effortlessly, as if the laws of motion have been suspended. In reality, the flashy acceleration is only half the battle. The quiet, patient, and equally powerful deceleration is the other half. And it is a half that carries the same impossible energy cost, the same fuel mass paradox, and the same technological hurdles. It is the silent partner in the crime of interstellar travel, and its price is just as high. Therefore, when we dream of fast starships, we must dream not only of the power to leave, but also of the power to stop. And the universe demands that the power to stop is exactly equal to the power to go. This fundamental symmetry is why our dreams remain just dreams. The energy and mass required for a round trip are so fantastically large that they place the stars forever out of reach for anything but the slow, patient crawl of generation ships or the one-way sacrifice of robotic probes. The deceleration problem is the final, quiet veto on fast travel, the universe's way of reminding us that every action has an equal and opposite reaction, and that for every leap forward, we must plan for the stop, even if we could somehow master the physics of acceleration and deceleration. Building a ship that can gently carry humans across the interstellar void, we would then face the most intimate and vulnerable frontier of all, the human body itself. Our biology, evolved for a very specific and protected planetary environment, is perhaps the most fragile component in the entire interstellar travel equation, and it introduces a suite of problems that no amount of engine power can solve. The two most critical issues are cosmic radiation and the effects of prolonged microgravity. Here on Earth, we are protected by a double shield, the planet's magnetic field and its thick atmosphere. These defenses deflect and absorb the constant, high-energy particles streaming from the sun and from deep space. Once you leave this protective bubble, you are exposed to a relentless rain of radiation. This isn't like the radiation from a medical X-ray. This is galactic cosmic radiation, consisting of atomic nuclei stripped of their electrons. Traveling at nearly the speed of light, these particles can tear through the human body, damaging DNA, killing cells, and significantly increasing the lifetime risk of cancer, cardiovascular disease, and cognitive degeneration on a long-duration mission, even within our solar system. This is a major concern for an interstellar journey lasting decades or centuries. The cumulative dose would be lethal without significant protection. Shielding is the obvious answer, but it is not a simple one. To provide protection equivalent to Earth's atmosphere, you would need a shield of water or lead several meters thick around the entire living quarters of the ship. The mass of such shielding would be astronomical, making the propulsion problem we discussed earlier infinitely worse. Lighter, more advanced materials are being researched, but there is no magic bullet. Magnetic fields, similar to Earth's magnetosphere, could theoretically deflect these charged particles. But generating a field strong enough and large enough to protect a whole ship would require superconducting magnets and immense power, adding yet another layer of complexity and mass. Without a revolutionary solution, the crew of a generation ship would be living under a constant, invisible shower of mutagens, with cancer rates soaring and the very real possibility of genetic damage being passed down to subsequent generations born on the ship. The second great biological challenge is microgravity. Our bodies are built to work against gravity. Our muscles, bones, and cardiovascular systems all require the constant pull of a planet to stay healthy. In weightlessness, astronauts experience a rapid loss of bone density, at a rate of about 1 to 2% per month in critical areas like the spine and hips. Muscle mass atrophies without the need for constant exertion, And the heart, no longer having to pump blood against gravity, becomes weaker. The fluid in our bodies, no longer pulled downward, redistributes, leading to head congestion, vision problems, and increased pressure on the optic nerve. The immune system also appears to function less effectively in microgravity. On the International Space Station, astronauts combat these effects with a rigorous daily regimen of several hours of intense exercise. But this only slows the deterioration. It does not stop it completely. For a multi-year mission to Mars, this is a serious but perhaps manageable problem. For a multi-generational interstellar voyage, it is an existential threat. The crew would need to live in artificial gravity for their entire lives. The only practical way to create artificial gravity in space is through centrifugal force, by rotating the ship or a section of it. This presents its own engineering challenges. The ship would need to be a large, rotating structure, like a spinning cylinder or a ring, with the crew living on the inner surface. The size of this rotating section is critical. If it is too small, the difference in gravitational force between the head and feet would cause disorientation and nausea. A comfortable rotation requires a large radius, which again means a larger, more massive ship. The complexity of building and maintaining such a rotating habitat for centuries is staggering. Every bearing, every seal, every structural component would have to be flawless and durable beyond anything we have ever built. A failure in the rotation mechanism could condemn an entire generation to the debilitating effects of microgravity. Beyond these two primary concerns, there are countless other biological hurdles. The psychological impact of confinement, isolation, and the knowledge that you are forever cut off from Earth would be immense. The closed-loop ecosystem would have to be perfectly balanced, recycling every drop of water and every molecule of oxygen without fail for centuries. A single pathogen or a crop failure could doom the entire mission. The human body is a complex, finely tuned system that we have only begun to understand, and it is a system that is exquisitely adapted to life on Earth. Asking it to thrive in a metal can hurling through the void for generations is asking more than we may ever be capable of providing. This biological fragility is, therefore, a fundamental limit. It means that even if we solve the energy, propulsion, and navigation problems, we still have to solve the problem of ourselves. We are not just building a ship, we are building a miniature, travelling Earth. And we are a long, long way from knowing how to do that. The stars may be waiting, but our bodies are telling us that we are truly children of this world, and leaving it for good may be the greatest challenge we will ever face, given the profound biological fragility of humans in space. It becomes clear that if we are to reach the stars within any reasonable time frame, we must divorce the mission from the limitations of the human body. This leads us to one of the few conceptually plausible methods for interstellar travel, the light sail. It is a brilliant and elegant idea, but its very elegance comes with a brutal and inescapable caveat. It is a technology that can only ever work for tiny, unmanned probes, not for the crude starships of our dreams. The principle is beautifully simple. Instead of carrying fuel, a spacecraft can use a giant, ultra-thin dot and highly reflective sail to catch the momentum of light particles, photons. Just as the wind pushes a sailboat, light pushes against the sail, providing a tiny but continuous thrust. This is not science fiction. We have successfully demonstrated solar sailing within our own solar system. The problem is that sunlight's pressure is incredibly weak, far too feeble for the immense push needed for an interstellar journey. The solution, therefore, is to bring our own wind. The proposed concept involves building an enormous, phased array laser based in our solar system, a light beamer of staggering scale. This laser would train its beam on the light sail of a distant probe, pouring gigawatts or terawatts of power into it, accelerating it relentlessly. Since the laser beam does not diverge much over distance, it can keep pushing the sail long after it has left the solar system. This method could, in theory, accelerate a probe to 20 or 30% of the speed of light, making a journey to Alpha Centauri a matter of decades instead of millennia. This is the basis for projects like Breakthrough Starshot, which aims to send gram-scale probes to our nearest stellar neighbour. And herein lies the first great limitation: scale. The energy required to push a spacecraft with a laser is directly related to its mass. To accelerate a probe the size of a microchip to relativistic speeds is a monumental challenge requiring a laser array that would be the largest structure ever built by humanity, potentially covering an area of millions of square meters. Now, imagine scaling that up to push a manned spacecraft, which would weigh billions of times more. The power requirement becomes absurd, equivalent to harnessing the total output of the sun. The infrastructure needed is so inconceivably vast that it relegates the technology to the realm of the very, very small. The second fatal flaw for human travel is the issue of deceleration. The laser push is a one-way ticket. It can accelerate the probe away from the solar system. But how does it slow down upon arrival? There is no giant laser at Alpha Centauri to fire a braking beam. Some highly theoretical concepts suggest using the light from the destination star to slow down. But the pressure from starlight is minuscule, utterly insufficient for any meaningful deceleration from a significant fraction of light speed. Other ideas are even more complex, like using a magnetic sail to brake against the interstellar medium. But these are unproven and would add mass, defeating the purpose of a lightweight sail. So, a light sail probe would be a flyby mission, screaming through an alien solar system in a matter of hours, its cameras and sensors frantically collecting data before it vanishes forever into the void. For science, this is valuable. For human colonization, it is useless. The third major problem is the sail itself. To be effective, it must be incredibly large, potentially kilometers across and impossibly thin, only a few atoms thick. It must be perfectly reflective, as any absorption of the powerful laser beam would vaporize it instantly. It must also be flawlessly sturdy, as any tear or wrinkle would cause it to fail. Navigating this gigantic, fragile sheet through the interstellar medium, with its dust and gas, is a nightmare. A collision with a single micron-sized dust grain at relativistic speed would rip a hole in the sail, likely ending the mission. Furthermore, keeping the laser beam perfectly focused on a sail that is billions of kilometers away is a phenomenal challenge in precision guidance. The slightest error in aim would mean missing the sail entirely, leaving the probe adrift. For a human crew, the ride would also be untenable. The acceleration, while continuous, would be very gentle. It might take days or weeks to reach even a fraction of light speed. All the while, the crew would be weightless, suffering the biological degradation we already discussed. There is no room for a rotating habitat on a light sail ship. The entire structure is designed to be as light as possible. So, while the light sail solves the propulsion problem for a specific case, it introduces a host of others that firmly confine its utility to robotic messengers. It is the ultimate expression of sending our senses instead of ourselves. It is a technology of patience and precision, not of speed and conquest. It acknowledges that the only thing we can afford to send at relativistic speeds is information, and the probe is merely the vehicle for that information. The dream of a giant starship with vast sails gliding on laser light is a beautiful image, but it is a physical impossibility. The mass ratios and energy requirements simply do not scale. Therefore, the light sail represents a bittersweet conclusion in our quest for the stars. It shows us a way to reach them within a human lifetime, but only by sending tiny digital ambassadors, not human pioneers. It is a technology that embraces the limits of physics rather than trying to overcome them with brute force. It is the realm of the physicist and the engineer, not the astronaut. So, while we may one day receive breathtaking images from a probe at Alpha Centauri, propelled by a giant laser we built, we must accept that we ourselves will remain behind, watching from afar, our bodies forever tethered to the world that shaped us, our journey to the stars accomplished by proxy. The light sail is a testament to human ingenuity, but it is also a sobering reminder of our physical constraints. It is a path to the stars, but not for us. After journeying through the overwhelming physical, biological, and economic barriers that stand between us and the stars, we arrive at a final, transformative idea. Perhaps the entire paradigm of space exploration as a physical journey is a dead end, a relic of an older way of thinking, and the true future lies not in moving our bodies, but in moving our minds. The only entity in the universe that we know can travel at the speed of light is information, light, radio waves, and data streams can cross the cosmos at the ultimate speed limit, unburdened by mass, inertia, or the need for life support. This fundamental truth points toward a radical shift in how we might experience the cosmos, moving away from the concept of a ship altogether and toward a future of virtual exploration and telepresence. Imagine a not too distant future where we have perfected robotics and artificial intelligence. We could send rugged, sophisticated robotic probes to other worlds, not as simple data gatherers, but as advanced avatars. These machines would be equipped with high-fidelity sensors, giving them sight, sound, and touch indistinguishable from human perception. The key technology would be a communication system with incredibly low latency. While we cannot break the light speed barrier for information, we can dream of technologies like quantum entanglement-based communication, which, if it could be made to work for transmitting information, might allow for near instantaneous data transfer across any distance. With such a link, an operator on Earth, or in a comfortable space station, could slip on a virtual reality headset and haptic suit and directly control this robot on a planet orbiting Alpha Centauri. The time delay would be negligible. You could look down and see the red dust of an alien world under your metal feet. Reach out with a robotic arm and feel the texture of a strange rock, and look up at a sky with two suns, all in real time. This is telepresence exploration. It removes the human body from the equation entirely. There is no need for generation ships, radiation shielding, or artificial gravity. The journey is made by a durable, expendable machine, while the experience of being there is transmitted directly to our senses. The risk is minimized, and the cost, while still significant, is a fraction of what a human mission would require. We could explore dozens of worlds simultaneously from the safety of Earth. This is not just a distant dream. We are already laying the groundwork for it with telerobotic surgery and remotely operated vehicles on Earth. The next step is virtual worlds. As our computational power grows exponentially, we will be able to create increasingly realistic and immersive simulations. Using the vast amounts of data gathered by telescopes and probes, we could reconstruct entire alien planets in perfect digital detail. You could put on a VR headset and not just see a live feed from a robot, but walk through a fully realized simulation of Mars, Europa, or an exoplanet. You could experience the crushing gravity of a super Earth or the gentle light of a red dwarf star, all from the comfort of your home. These virtual worlds would be limited only by our data and our imagination, and they would be accessible to everyone, not just a handful of astronauts. This democratizes space exploration, turning it from a physical endeavor for a select few into a sensory experience for billions. The most speculative, and ultimately the most profound, shift would be through the concept of consciousness upload. If the essence of a person, their memories, personality, and consciousness could be digitized, then that information could be transmitted at light speed across the galaxy. A digitized consciousness could be beamed to a receiver on the other side of the galaxy and installed in a synthetic body or a virtual environment, effectively achieving instant travel. This concept swaps the immense challenges of physics for the currently insurmountable challenges of neuroscience and computer science. We have no idea how to digitize consciousness, or if it is even possible. The ethical and philosophical questions are staggering. Would the transmitted copy still be you, or would it be a new entity that simply believes it is you? Despite these unknowns, it represents a theoretical endpoint where the only thing travelling is pure information, the pattern that makes a person, leaving the biological body behind as a shell. This paradigm shift redefines the very meaning of exploration. For centuries, we have equated exploration with physical travel, with the journey of a body from one point to another. But the universe seems designed to make that kind of travel impossibly difficult for biological beings. It is, however, perfectly designed for the transmission of information. The future of space exploration may therefore look less like Star Trek and more like the internet. It will be a network of sensors and experiences, a cosmic web of data that we can tap into and immerse ourselves in. The romantic age of the astronaut as a rugged pioneer may give way to the age of the explorer as a digital tourist or a remote operator. This is not a lesser form of exploration. It is simply a different one, and arguably a more intelligent one. It works with the universe's rules instead of fighting against them. It accepts that our bodies are frail and rooted to Earth, but our minds, our curiosity, and our sense of wonder can travel to the ends of the cosmos at the speed of light. So, the reason we will never have starships as fast as those in the movies is because we won't need them. The ultimate spacecraft is not a hull of metal with a roaring engine. It is the silent, swift, and boundless transmission of data. The final frontier is not a place we will physically visit, but an experience we will all share, virtually and instantly, from right here at home. The dream of touching the stars remains, but the hand that reaches out may be made of light and code, not flesh and blood.